Hello, Dilip. Hello, audible?
Yes, sir. Audible, sir.
Please make me host.
Okay, sir. Just
Dilip, now presently I am using digital this writing board, not this physical board.
yeah, sir. Already said, sir. Skills.
Okay. Yes, please. Okay, so already this first chapter and DC machine we have complete first chapter we have started, and one numerical which was asked in your ETU exam recent pattern we have discussed. Okay, any doubt up to here? Yes, please. Okay, dear, we discussed this RLC. Okay. Now, like this is a RL circuit. Okay, dear. Hello, audible.
Yes, sir.
So now we proceed further. Today we discuss the to solve numericals on this we have to know there is a different type of series combination circuit mostly. Even they ask in parallel now. Okay. Here first is if we connect a pure resistance with a coil. Coil means L inductor. It is RL series circuit. RL series circuit. Next is maybe there is a or practical coil, because ideal coil is not a pure inductor. It may be resistance also, that is considered in series with coil. The equivalent circuit of a, suppose you have a solenoid coil, then they have a resistance and inductance, because this coil is consist of wire, so it has a resistance also like this. Okay, so actually this is a coil, practical coil. Okay, this is a coil. Okay, now if we connect a R and C in series, so it's known as a RC series circuit. There is a third RLC series circuit. Okay. So here there is a resistance and a inductor in series. Here there is a resistance and capacitor. Okay. If there is a all three components like a resistance, inductor and a capacitor, it form a RLC series circuit. Okay. So when we apply the AC, when we connect to AC sinusoidal voltage source here, all these three circuits. Okay. My dear, this is R, this is L, this is R, this is C, this is R, L, C. Now, when we apply the voltage, that is pure sinusoidal voltage, means that wave is the Vm sin omega t. Here is same also, okay, with the frequency f hertz, okay, frequency f and voltage is this, okay, Vm sin omega t. Here also V equals to Vm sin omega t. Okay, dear. Then due to this, there is a response. Response means the current is flow in the circuit I. If you apply a sinusoidal voltage, then there is a current is also sinusoidal. Okay. Then it produces the voltage drop in the circuit. Okay. The voltage across R, drop across L. Then total applied voltage is V. And always here we write this capital letter, it is a RMS value of source voltage which is applied across the circuit. Same like here, due to this current, there is a voltage across R, voltage across C, and total is applied, it is capital B, suppose, okay? Total voltage across, this is a source voltage. Same like here, due to current, there is a voltage across R, voltage across L, and voltage across C. If we see the vector diagram of this, so suppose we consider the current in series are in the same. So let us we take a current as a horizontal reference phasor. Now, due to this current, there is a drop in this resistance, IR. Basically, actually IR is greater. Now, this current, here we saw this is your current, okay? Due to this current, the drop in resistance are in phase with current. It means here phi in phase difference is 0 degree. Okay. Phase difference is 0 degree here. Now, drop in inductor, it is perpendicular to this current voltage drop in resistance like this. This is VL. Now if we calculate a total, that is the vector sum of these two. This is this, okay? This is your total voltage V. Now you know total source voltage and source current. Hello my dear. This is your source voltage. This is your source current. Now total voltage and total current, this is the phi angle. Okay, for resistance it is 0, but total, if overall we see, what is the overall power factor of circuit is, phase angle is phi. Then cos phi will be your power factor of the circuit. Okay, power factor angle phi. Okay. Now you know if we calculate here total voltage equals to voltage across R plus voltage across L. For total means it is IZ. Z is the impedance of the circuit. Okay. So due to this, there is this is your reactance, inductive reactance. Okay. So here it is drop in resistance. This is the drop in reactance, inductive reactance. So I. If we take I common, means this Z is combination of this both. Now because they are out perpendicular, they are not in phase. So it is not a algebraic sum. It is a vector sum, or it is a complex number. Means Z is a complex number. Okay. Complex number has a real part and imaginary. This is called as a real part. This is known as a imaginary, J part. Okay. Imaginary. Okay, imaginary part. Real, imaginary. Now if we calculate a magnitude, now this form is called as a, okay, this Z equals to R plus JX plus minus. It may be your imaginary part may be negative, positive. Okay. So it is called polar form. Polar form. Okay, already we discussed. And if we denoted with more Z, here if we calculate a Z, means your impedance triangle is, this is R, this is your reactance. Okay, XL. So this is your Z, inductive reactance. Okay, this is your again phi. Okay, this is Z, impedance triangle. Okay, so Z equals to, if you calculate by Pythagoras, R square plus XL square. This is the impedance. Okay, Z. And angle we can calculate this phi. You know, tan phi. R by Z, the tan inverse, this phi equals to tan inverse real part to imaginary part. Okay. Then we can denote this Z as a polar form. Magnitude and angle. This is called magnitude, or this is phase angle. Okay, this is called polar form. So in calculator, we can convert here to here or either here to here. Okay. Generally, parallel circuit, AC circuit network, we solve with polar and rectangular form. Okay.
Sir, H by R was
Yeah. Now, if we talk about this RL, here it is all same, but here this Z is R plus. Actually, here it is a capacitive reactance is minus J XC. It is a negative because here current is lead, voltage is lag. Okay. Please, capacitive reactance is negative always. Okay.
तो ये phi is equal to 10 minus 1 ये x upon r होगा या r upon x में?
Oh, sorry, imaginary by real part. Imaginary by x by r. R by Z is the power factor. Yes, perpendicular by 10. No? Okay, yes. Yes. X by R. Sorry. Next. So this is your capacitive impedance, okay, in this circuit. Actually here, this is suppose current, this is your voltage drop in R, VR, due to your current, this is suppose your current, I, is 0, we take it as. Now drop in resistance always in phase with current, but drop in reactance, this capacitive reactance, XC. X equals to 1 by omega C, correct? XL equals to 1, it is omega L. Okay, omega is a frequency that is in radian, 2 pi RL. This is 1 by 2 pi FC, okay, in ohm. Now, due to this, actually this drop is, this is the VR. Now drop it is lag. It is lag, okay. IX means VC. Okay. IXC means VC, okay. This is IR. Okay. Then means see, if we check here, if we put this vector here, इसको इधर ही दिखा सकते थे. Due to this current, this is here. Okay. This VC equals. Now this two vector, the vector sum of these two voltages will give you, like we put a same parallel vector. This will give you. Okay, this is your total voltage. This is your total source voltage. Now this angle, phase difference between source voltage and source current. Okay. So again here, your total voltage equals to voltage across R, and it is a negative, means like it is minus plus and minus VC, because it is downside. This is positive. In in your quadrant system, this is positive. Please move that. Sorry. Okay, so this downside is negative. That's why we put a minus VC, or it is V equals to in vector sum IR. This is IZ, okay? IZ. Then this we can minus JIXC, okay? Or II cancel, then we can put J equals to R minus JXC, okay? Correct, like this. Now we come to the, when all these three components are in circuit, okay? So let us, this is the current in same, this current is in same through this all the components through R, L and C. Due to this, the drop in, okay, this drop in due to this current, drop in resistance in phase with current, but drop in reactance, do this reactance, inductive drop, it is upward, okay, like this, and this is downside due to negative, okay, VC. This is VL. Now, if we calculate the resultant total voltage, then this is negative side, so this part we subtract from here, okay, this equals to this, okay, then this will give the difference. Okay, it depends if you are which is higher value, okay, inductive, if your circuit is inductive or your circuit is overall it is capacity, so sometime it is VL minus VC is come negative also, means this side, so it means it depends on the values of L and C, it may be lagging or leading power factor, okay, means inductive or capacitive, but let us general case we take a L is higher, means inductive, most of case mein circuit is inductive. So now if we calculate this total, it comes like this, okay, so this will give you V. Now this is the phase difference, voltage and current phi, okay. If we now calculate a total V equals to VR, this vector, plus VL minus VC, okay, vector sum, or it is IZ equals to IR plus I XL minus XC, okay, vector, or we can write I cancel, then Z equals to R plus XL minus XC, as a polar form, rectangular form we can write JXC, or magnitude of Z impedance is under root R square plus XL minus XC whole square. Okay, this is the impedance. If we calculate a current, then total voltage by total impedance. Okay, Z. If we put a polar form, generally voltage we take as a reference 0, then impedance as a phase angle. Then resultant current will come with magnitude and phase angle. And if we calculate the power factor, the power cos phi of this angle will give you power factor. Okay. Also, because current may be, in this case it is a lagging, current is lagging, angle is positive. Okay. If angle is negative comes, this power factor is leading. Okay, dear. Now we discuss the next one case, resonance in AC circuits. Okay. Actually, this resonance occurs when there is either it is a series RL circuit or parallel, maybe in parallel. Okay, based on the circuit series parallel, resonance circuit is also classified as a series resonance, parallel resonance. But first of all, we understand the resonance. Resonance actually it is nothing but it is a condition in an AC circuit, in any circuit, when net reactance of circuit becomes 0, X equals to 0, means or inductive reactance equals to capacitive reactance. This is the condition of resonance. Now, if suppose it may be occurs, it means the circuit is under resonance, or at this circuit become resonance. Now, to make this XL equals to XC, we can achieve this condition by vary the frequency. Okay, so suppose first case में we this series resonance or resonance condition in series RLC circuit. Okay, so means we suppose we consider a R L C series circuit. Okay, now we discuss here resonance condition in series RLC circuit, R L C. So where here when we apply a AC sinusoidal voltage, okay, that is V equals to Vm sin omega t. Due to this, there is a current will flow. Okay, when do this current, there is a drop in this, drop across this, and drop across VC also. Okay, under resonance, what happen na? If circuit is under resonance, means suppose there is a frequency F. Okay, this is the frequency. Now this frequency is the vary from 0 to infinite. We can vary. So between this variation, if one particular frequency will come F naught, that is called resonant frequency. Resonant frequency or frequency of resonance under resonance condition. So if we vary the, suppose these values are fixed, we vary the frequency, then we can achieve the resonance condition at some particular frequency, that is called resonant frequency. Or we can say omega naught. This is also resonant frequency in radian per second. This is in cycle per second or hertz. Okay, you know, omega equals to 2 pi f. It is in radian per second. Okay. If not, then not. Okay. Correct. So at resonance condition, actually, if we draw, this is your current, suppose in the circuit at resonance condition. Then due to this current, there is a drop in resistance. It is in phase with current. Okay. It is in phase with current, but due to inductance of circuit, there is a drop. There is a due to this. See this. Means if see current is same. Now if due to this inductance XL, due to this capacitive reactance is XC, if at resonance condition they become equal, it means drop across this, na, means VL and VC become equal. But they become actually at resonance frequency, it is considered as VC naught. Naught means actually the current through resonance condition is also denoted by I naught. Current flowing through circuit under resonance condition, that is I naught. Then it is I naught XC. Oh, sorry, XL. This is I naught XC. Okay. This is XL. Okay, please. So these are equal. It means total voltage in this case, this total voltage is appear across resistance only. Means if this circuit total voltage V will, sorry, this is R, across this. There is also voltage across VL, VC, but they are opposed. if we calculate the net voltage across this will be 0. And entire voltage is come across this resistance at resonance. Why? Because they are equal and opposite, then VL minus VC 0. Okay, under resonance. Got it? Okay, dear. Now this is under resonance condition. This is the phasor diagram of circuit, RLC series circuit. Now see. Now if we impedance triangle, we make a impedance phasor. So this is your resistance R, and due to these are your reactances. Okay, XL, XC means they are equal and opposite. You know, this is equal. This is equal and opposite. Okay, it means 0 XL minus XC. Then total impedance is Z only. Okay, dear. So now if we calculate under resonance, please see at resonance condition. If we calculate the impedance of circuit, first you calculate impedance. Z is equals to under root R square plus XL minus XC whole square. Now this is 0 because they are equal. It means Z equals to R square. It means R minimum. कैसा रहेगा ये? Minimum. Okay. Impedance of circuit under resonance is, it is minimum. Okay. It is minimum. Now second is we calculate a current under resonance. So you know I equals to V by Z, and you know your Z is only R. So it means it is maximum, current is high, impedance is low. So it is a maximum. Maximum current will flow, okay, through the circuit. Okay, and it is denoted by I naught. Current under resonance condition. Now third is if we calculate power factor. Power factor means cos pi is R by Z ratio. Now R, Z are equal, it means 1 unity. Okay, so under resonance condition, your circuit is behave like a pure resistive circuit. Okay, dear. Next, if we calculate the frequency of resonance or resonant frequency, resonance or oscillation, okay. See, XL equals to XC, or it is omega L equals to 1 by omega C, but it is at particular frequency omega naught, or omega naught square equals to 1 by LC. Correct now? Omega we take this side and L. Then omega naught equals to, you know, if we do root, then it becomes 1 by under root LC. Because root of 1, it is 1. It is in radian per second. This is the resonant frequency. Or either you write 2 pi F naught equals to this root LC. Now L and C are in, this is in, it should be in Henry. Okay. Inductance. C is capacitance in farad. Please. Okay, unit. Then it comes in radian per second, or F naught equals to 1 by 2 pi under root LC. So this is in hertz or cycle per second. Okay? This is the frequency of resonance at this which resonance is occurs. Okay. So now this how this we have actually see. Suppose here we take a different like components, circuit parameters, like what are the parameters? Resistance, inductive reactance, capacitive reactance, impedance, current, power factor, whatever it is. Okay, this thing. And when we vary if we take here on this axis, we take a frequency. Okay, if we vary frequency from 0 to infinity, okay. Then if we see resistance of circuit, it is a fixed value, it is independent of frequency. Okay, so R is fixed. But your inductive reactance, it is direct proportional to frequency. As we increase the frequency, at 0 frequency, 0. So it is linearly, it will vary. Okay, like this. This is XL equals to omega L, direct proportional. And capacitive reactance, it is negative. X equals to minus J by omega C. Okay, it is negative. So it are inversely proportional. So at when frequency omega is 0, it is at 0 it is infinite. So here it is start from here, and at infinity it becomes 0. So it is like this. Sorry. It is your XC equals to 1 by omega C, negative. Okay, this is negative axis, this is positive values. Okay, now if we calculate their combined net reactance XL minus X, so because this is positive, this is increasing, this is decreasing, then at some particular frequency, when they become equal, this part and this part. Okay, so here at this particular frequency, this point, okay, this part and this height is equal, means inductive reactance, capacitive reactance, it is at F naught or omega naught. Okay, because this axis is your frequency, so this become equal, and at here it is a reactance is 0. Okay, correct. Now if we talk about the Z impedance, so Z equals to under root R square plus XL omega minus 1 by omega C. So when 0 frequency, when omega is 0, see which is infinity, this part is infinity. When means this part infinity means this impedance is infinity when at 0 frequency. So means and it is here. So your capacitive, and at resonance frequency this become equal, so only R. So it is like this way, and it is again increased. At infinity frequency, this is 0, but this will be infinity. Actually, your impedance is very like this way. This is your Z. Now, here na, sorry. Okay, so at this point here, see, this at from here, this side, this circuit is capacity initially. Capacity means it operated leading power factor. Here is your power factor is 1. Here it is lagging, less than, sorry, leading. This side leading. Okay, it is here unity. Then this side is lagging because circuit become inductive. Okay, it means this is impedance is inductive due to inductance. This is for capacitance. And you know, at resonant frequency, like this. Okay, so see, so at this point your impedance is minimum, means equals to R. So here Z equals to R at this point. Okay, now if we talk about the current, when impedance is infinity, current is 0. But as impedance is decreased, current is increased, and it is at this point it is a peak value. Then again it is decreased. So this is your current. This is current. Now this current is your, what is this value? It is a I naught, maximum current at resonance. Okay. So these are the parameter variations. This is for series resonance. In parallel, it is just opposite. Okay. We take you, there is a like susceptance, and your impedance is admittance. Okay, we use the parameter resistance is okay, but you know, 1 by resistance is conductance, that is denoted by G. 1 by X is susceptance, that is denoted by B. 1 by Z, it is denoted by admittance, it is Y. Okay, conductance, this is susceptance, this is admittance. Okay, got it. So this parameter we use for parallel resonance. Now there is a one question they ask in most time in class 2, difference between series and parallel resonance. Okay. Okay, I put in group to read this difference between this, okay, parallel and series resonance. So when the condition is occurs in parallel circuit also. Okay. Now why we explain, because there is a questions asked on this resonance also. Okay, that's why we discuss this. Let us discuss now numericals on this. So this root mean square value and define the waveform, form factor, frequency, these things we discussed already. Okay. Now come to the next. What has a greater equivalent resistance if two equal capacitor in series or parallel? And this is one numerical is given, a series RL circuit. Okay. You know this or we solve this? Hello? Yes. It is required to solve or okay?
Also, please.
Yeah. Because we have now questions are increased. Earlier only this questions only, but now maybe because portion is we have to cover the lot of things. It is okay. You know this how equivalent resistance, actually it is asking reactance when two capacitor in series or parallel. So let us be complete, not an issue. Second question of this. Second में part है, you know.
So all these questions are from the old question paper, right?
Yeah, this is from old one, oldest. Okay, ETO.
Okay.
So here, in second part, suppose we provide a solution here. Okay, solution. It means when two equal capacitors in series or case, this is a case one, case in first case. In case two, when two equal capacitors in parallel. Okay. So suppose there is a two capacitors C1 and C2 are connected in series. First of all, we calculate total equivalent capacitance. We are not calculating first resistance, means reactance or impedance. First we calculate the capacitance, that is unit is farad or microfarad. It is equivalent capacitance in parallel, so it is just opposite to resistance. In series, it is how we calculate. In series, we denoted total equivalent capacitance in series, CSC, equals to 1 by C1 plus 1 by C2, or in parallel it is C1 C2 by C1 plus C2, like this. Okay, 2A. Okay, but C1 equals to C2 equals to C. This is given in question condition. Therefore, CSC equals to CC C square divided by 2C, or it is C by 2. Okay, this much. Okay, and total reactance of circuit, or it is a resistance, because both have a same unit, no ohm. Total resistance or reactance actually. In series it is X CSC, yeah? Equals to 1 by omega CSC. If we put this value, so it becomes 1 by omega C by 2, or it is 2 by omega C. Okay, this is 1. But when this capacitance are connected in parallel, when in parallel, total capacitance, total equivalent capacitance, that is CP, suppose in parallel. So it is just like C1 plus C2. Please, it is just opposite to resistance. Okay. Then CP equals to, because C1 equals to C2, so it comes 2C. Okay. Because C1 equals to C2 given, okay, equals to C. Therefore, total equivalent reactance or resistance in parallel circuit XCP equals to 1 by omega CP, or value of CP is 2C. It means 1 by 2 omega C. So my dear, first capacitance is more in parallel and total capacitance in series is less. But if we talk about resistance is higher, means reactance. Now if we compare, this is equation 2. So now if you write here from equation 1 and 2. So this suppose equation 1 is divide with this 2. It means it is 1 by omega c as c divided by 1 by 2 omega c means sorry. It is omega cp. Okay. Or so directly you can put the value. This comes 2 by omega c, na? So it comes 2 by here 2 by omega c, and here it is this come 1 by 2 omega c, or equals to 2 by omega c. We can change into multiplication, then 2 omega c by 1. Okay, so omega c cancel. It comes 4 raised to 1 ratio. Means x c s c in series, reactance in series is 4 times of reactance in parallel. Which is greater? XCE is greater than XCP. Okay. Okay, dear. Next is second question. It's B part. A circuit has a resistance. There is a resistance in a circuit. Inductance. The voltage across its end is here. Apply the 60 volt, 50 hertz. Calculate L is 0 Henry. Okay. What now is asking impedance, power factor, and power absorbed. My dear, due to this voltage is applied, current is there. Now always this voltage is written, na? It is RMS value. So we get a RMS value of current, then impedance. Okay. So first to calculate the impedance, you have calculate inductive, resistance of circuit is 3 ohm. Then inductive reactance, this is a resistance. Then inductive reactance. XL equals to omega L equals to 2 pi FL, or it is 2 into 3.14 into 50 into 0.01. My dear, this is become 2 into 50, 100 into this 1, then it comes 3.14 ohm inductive resistance. Then now we first calculate impedance. Impedance of circuit. It is directly we calculate magnitude R square plus XL square. 3 RL. 3 square plus 3.14 whole square. Root of this equals to
4.3, sir.
yes, square root of this yes, it comes 4.34 343 ohm. Okay. Now we calculate current. Current is not asked, but it is required. The current of flowing through circuit I equals to voltage by impedance. It is a voltage is 60, impedance is 4.343. $13.82 we can write as or 16. Then we calculate, he is asking power factor. You know, power factor of a circuit is nothing but it is R by Z ratio or phase angle, cosine of phase angle. And it is R is 3, Z is 4.343. This ratio will give you 0.69 lagging, okay, power factor. Now fourth, they ask the power absorbed. Absorbed means dissipated. It is, P equals to I square R, or it is VI cos pi. I square is 3.8 watt. Okay, dear. Question number 3. He said that a coil having a resistance and inductance, practical coil. See, suppose this is a solenoid coil, like this. So this coil, because it consists of a wire, so it has a resistance. So this equivalent circuit, if we draw now, this coil, okay, it has a resistance and reactance. So this, Yeah. So this equivalent circuit of this, it has a resistance and reactance, inductance. Okay. The inductor. This is a coil which has a resistance. This coil resistance is 10 ohm. And inductor, it has an inductance is 0.15 Henry. Okay. This coil is connected in series with a capacitor. So suppose it connect with a capacitor here. Okay. Now across this, now this circuit end, now we apply here voltage. It is 100 volt, 50 hertz supply, AC supply. Due to this, there is a current will flow in the circuit. There is a voltage. Now we consider overall as it is a RL circuit. It is voltage across R of the coil, inductor of the coil on capacitance. This capacitance value is not mentioned. Actually, we not required also. And the total voltage here, it is 100 volt applied. So now we say that if there is a condition is given, if current and voltage are in phase, what will be the current in the circuit and voltage drop across coil? Now coil is up to here, my dear. Coil is up to here. So this is asking voltage across the coil. Second part, okay. When we calculate the current, we can calculate the voltage drop across the coil, okay. So first of all, when we solve this, okay, give the solution. Since you write here, since as current and voltage, circuit current and voltage are in phase. Are in phase. It means circuit under resonance. Okay. So you know at resonance, now you write at so we consider as a RLC series circuit. So at resonance, you know, inductive reactance equals to capacitive reactance. Okay. So now here we calculate a capacitive reactance. Sorry, inductive reactance. Inductive reactance. Reactance of coil XL equals to omega L equals to 2 pi FL, or it is 2 into 3.14 into 50 into L is 0.15. No? What value will come? Yes, please. It comes 47.1 ohm. Okay, and both will be same. Okay, at resonance this much. Correct? Inductive capacitance. Therefore, we can calculate a total impedance of circuit Z under this condition. So as you know, this is 0 equal. It means it is R only, or it is 10 ohm. So your circuit impedance will be, now this is a resonance condition. If voltage and current are in phase, means circuit is at unity power factor. Hello, this condition will tell you it is a resonance condition. Okay. So now this is the resistance impedance total. Now we can calculate a current. Current through the circuit. Circuit is asked, no? I equals to V by Z. That is 100 volt by 10 ampere. It comes 10 ampere. 100 by 10. Okay. Now the next part. Hello. Actually, they ask only first. This is the first part. Okay. Part 1. In part 2, he asked VD, voltage drop across coil. Okay, the coil has a resistance, and so my dear, you know, coil means first if you calculate, see, voltage across coil resistance, it is this VR. Voltage across coil inductor, this. Then there's sum. Actually, please do not we do like this VL plus VR. It is algebraic sum. Here it is not algebraic sum. When we do the algebraic sum, then both are in same phase. But these are vectors because they are not in phase. They are perpendicular to each other. Then we calculate this is the total of this. This will give you voltage across coil. Okay, dear. So how we calculate a voltage drop across coil? So individually you calculate VD across coil inductance or coil resistance. It is IR. Okay, this is IXL. Then you could do this, or there is another method. Okay, you have to calculate a coil impedance or impedance of coil. Coil means your coil as it is a resistance and reactance. Now it is not an impedance of circuit. This circuit impedance is R only, 10 ohm. But now we consider this circuit up to this part only, this up to this. So it is like a series RL circuit, means inductor only. Okay. So like impedance of coil means, so there is a coil resistance plus axle. It is a series RL circuit. Okay. So very simple. 10 square plus 47.1 का whole square root How much we get? It comes
48.15.
very good. Very good. Sorry. 1.5 we can write that. 1.5 ohm. Now, therefore, VD, voltage drop, that is IZ of coil. Coil drop across coil, that is V coil. IZ of coil, okay. Or it is current is 10 ampere into it is 4815 into then it comes 481.5 volts. Okay, so at resonance there is a, if you add the voltage here to here, it is almost 500 volt. What we apply here? 100 volt only. Sorry, 100 volt only. But we get a voltage across inductor is 480 volt. Okay. But if we calculate here to here, then total will come only 100 because this is opposite. This both are equal. Like voltage across coil, inductor, and voltage across capacitor, they are equal and opposite. This is plus, this is negative. Okay. Okay. That's why earlier we use a chalk for electrical, chalk for conventional FTL fitting. So that at starting it produce a surge voltage, high voltage for ionization. Okay. Got it? Easy. Next one, another problem. This was question. It is already, it is in MET also. It is asked in ETO. There is a parallel RL circuit. Now in this, we see here. ज़्यादा लिख के फाइल बड़ी हो जाती है तो ये थोड़ा तकलीफ देता है. Here in this now, this other question tomorrow we discuss. Okay. Here see, this is the one question. It is asked in your this also. Okay. Yeah. Same question. Where it is question number 4. यहाँ पर ये कौन सा क्वेश्चन था? Here it is 4 ना? Fourth question. So we discuss this. This is the question number of this MET जो class 2 में आते हैं, but they are also asked in your ETO. It is already asked. That is the 4th question. here capacitor, inductor. It is RLC parallel circuit. Okay. Here R L C. R is here 50 ohm. L is 0.15 Henry. This is 100 microfarad. Okay. Now here AC source is there. It is 100 volt, 50 hertz supply. And this is the total current. Here source current total. Okay, at this node, now it is a current is divided here in three part. Let us in all branch, branch 1, branch 2 like this. Okay, it is suppose I1, this is I2, I3. Okay, or it is in R, IL or IC. Now you know we can represent this is a suppose Z1 branch 1 impedance, branch 2. In AC we use a impedance. Okay, third and sorry 2 and 3 impedances. Okay, so actually we can directly we also do, but better if you do with the polar and rectangular form, so that we get the power factor also easily. So just you can easily, you have to calculate. First of all, branch impedances. Just you write the impedance of branch Z1, Z2, Z3. You know Z1 means it is a R only. Here R na 50 ohm. Imaginary part here J0. Okay, imaginary part is not there. In Z2, if we write there is a 0 real part, but imaginary is there. Na? So first you calculate. Hello, what is the XL? What is XC? XL equals to already we calculate na omega L 2 pi F L. So this value will come same like it is 40. Please you have to calculate. One, it is 0.15 H na, already we calculated this. And this is we can calculate 1 by omega C. It means 1 by 2 pi F C. Or this value will be, how much it comes? It is 2 into 3.14 into 50 into 100 and into 10 raised to power minus 6 microfarad. No? When this 6 it come up, it is 10 raised to power 6 divided by this. It comes 5, 10, even 100 also. This 1, 2, 3 on this 5 to the 10, it comes this. Okay, into 3.14. So this 3 cancel na, so it comes only 1000 na, only here 30. So 10 raised to power 3. Okay. So if you divide this, what value we get?
31.83, sir.
30.
31.83.
1000 100 by कितना आएगा मैम? 60 ना, 1 2 3 4, so 2 only na here, 2 only remain. Okay, it is 100 only okay, it means 100 by this we get a 31.85. Okay, ohm. So here you know this part is 0, but J part is plus 31.85. 847 means okay. And here, oh no, this is 47. This is J 47.1, and this is 0 minus J 31.85. Okay, dear. This okay. All three impedance. Now you can write their polar form. Okay, their polar form we can write Z1 angle phi or theta, theta 1, their angle. Z2 angle theta 2, Z3 angle theta 3, their polar form. So you can calculate, you direct convert, it comes 50. You know, pure resistive, this angle is 0 degree. This is, you know, in pure inductive, it is your current is lag by 30, then impedance is lead. Okay, so it comes 47.1 angle 90 plus 90 degree, and here it comes 47.1 angle, you know, 31.85 angle is minus 90. Now if we calculate now branch current is asked, branch current. Okay, so first if we calculate in I1 means IR in branch resistance, so it is you know, voltage, this voltage we take a reference voltage. Okay, V naught. Okay, so I1 means it is your supply voltage, because voltage across each it is same, no? 0 by Z1, or it is angle is theta 1. It means it is 100 angle 0 divided by your 50 angle 0. So 0, you know, in division it is subtract your angle. 100 by it comes 2 ampere. Angle is 0 degree. Okay, this much ampere. Current is in resistance. Then in it is also known as a resistive current. A current through resistance. Now current in 2, again it is means 100 angle 0 V by Z2, and now Z2 is 47.1, angle is 90 plus. Now if this angle is go 0 minus 90, then there is a negative current. Okay, so 100 divided by 47.1, my dear, it comes 2.12 ampere. Angle is minus 90, means current is lag in inductor. Okay, this much. Now I3, again it is V by Z3. It means 100 angle 0 divided by 31.85. Angle is minus 90. When this go 0 minus 90, it is plus 90. Okay. So here it comes 100 divided by 31.85. 3.139 or 14 we can write as. So 14 भी लिख सकते हैं. Okay, this much. Angle is 90 plus. So see, this is IC because its current in capacitor is lead. Current in inductor is lag by minus 90. Pure inductor, pure capacitor, and this is a resistive current. It is in phase with voltage. That's 0. Okay, now you can draw the vector diagram. So in parallel circuit, you know, voltage is reference because voltage is same. In series, voltage is current is same. So this is your V0 0. Okay, angle 0 V0. Now due to this voltage, the current in resistance, it is in phase with this voltage. So it is IR. But current in inductor, lag. So this is your lagging current, okay? And it is this much. It is 2.12 ampere. This is 2 ampere. Huh? Now current in capacitor, it is leading here. Current is leading. And it is higher value. You know, this is IC. This is IL. Yeah. This is your 3.14. So this is, you know, plus 90, positive. This is negative. It is lagging. See, this lag the voltage. This lead the voltage. Okay. My dear, this current are opposite. So if we subtract this part, okay, so here we get IC minus IL. IC, yeah. And this is your resistive current, okay. So if we calculate their resultant current will be, you know, this is your resultant current. This is your resultant current, that is total current. Now how we calculate a total current? It is a vector sum of IR plus IC minus IL whole square. Okay. You can calculate. And it is, you know, it is leading with this phase angle. This is the phi. Because this is your voltage, this is your current. Total current, total voltage. Okay, so resultant current is leading, power factor is leading. But if they ask power factor also, so this is one method to calculate this total current. This we can calculate, okay? You put these values, okay? Or other method you calculate in, this is a first part, branch current. In second part, already time is over. See, in second part you calculate a total impedance of circuit. Total impedance is Z1 plus 1 by Z2 plus 1 by Z3. Okay, when we calculate total Z, then source current equals to total source voltage divided by total impedance, and it comes in polar form. Okay, phi. This is 0. then your current will come with angle, okay, phi. And then power factor you can also calculate by cos phi. Cos sine of this angle will give the power factor also if they ask, but in this question they not ask. Okay, dear. Either you do by this method or by this method you can calculate a total current. Okay.
Or directly
Hello?
you can add this.
Yeah.
You can add directly 3
What?
directly.
What your voice? Hello. Your voice breaking. मुझे इतना सुना है कि एक्चुअली शेयर इन ग्रुप है. Okay. Okay, good night.